Hey everybody, welcome back. We're on to our final episode related to the hydrolysis unit here on Bennett's Chemistry 12 tutorials. Couple of things. Number one, the next episode is going to start into the unit of titration, which should be pretty interesting because titration is a laboratory technique. And as you can see, we're clearly not in a classroom or a lab environment. We happen to be in an evacuated or emptied room in my house during our quarantine period here for the COVID-19 pandemic. So it could be interesting. We'll see how that goes. Obviously, it's going to be all theoretical. I'm going to mention a few things. I'm going to try and draw pictures on the board to demonstrate kind of what you would be doing. But a lot of the titration unit is actually the doing. It's the experimental technique. So obviously we're going to miss out on that. Hopefully you've had an opportunity to do a titration before you've actually been able to manipulate things. So when we get to that, I'll be talking about that, and hopefully you've had that opportunity at some point in your chemistry career. I'm going to guess you did in Chemistry 11. Most of us do get that opportunity to do it in Chem 11, and I know that when I teach Chem 11, I make sure that my students have that basic titration skill going into grade 12 so that they can kind of hit the ground running when we get to the titration unit. Anyways, that will start next class, and it'll be very theoretical. And you might say, well, titration last year in Chemistry 11 was pretty straightforward. How difficult can it get? I mean, you take a burette, you take a sample in an Erlenmeyer, and you mix the two until you get the color to change, and then you're kind of done, right? What's there to it? There's way more theory to it. Now that you know way more about acids and bases, there's way more that we can introduce from a theory perspective. So it does get quite a bit more complicated, okay? So anyways, that will start next class. So today is going to be like I said, it's the last class of hydrolysis, and you can see over my shoulder that the topic is the hydrolysis of anhydrides. And so we'll go through a couple of things. Number one, obviously, we're going to define what is an anhydride. The basic kind of principle of this thing. And then we'll get into, okay, so once you've kind of identified what those anhydrides are there categories of them, and do the categories of them do different things out there in the chemistry world, which they do. So you will learn those things. A really important part of this is it's very qualitative. There are going to be no numbers associated with this. There won't even be equilibrium constants associated with this. It's just there's too many kind of competing equilibria here, and too many times where things aren't reacting 100%. So what we're trying to do is we're just trying to give you an idea of this is what they do, and maybe here's why they might be important to you from an understanding the world perspective, because you'll see there's practical application for a lot of them. The implications they have to chemistry in the chemistry lab, but also just kind of having an understanding of, in particular, the environmental impact of these things. Okay, so first thing, what is an anhydride? An anhydride, by kind of definition, means without water, so the removal of water from something. So if something has water and you remove water from it, it ends up being an an without hydride. Okay, so let me give you an example. So an example of an anhydride would be calcium. I'm just going to write it down here. Calcium hydroxide. That is an anhydride. Now, why is that an anhydride? So keep kind of in your mind that calcium oxide is the anhydride. Well, if you were to take calcium hydroxide and you heat calcium hydroxide, like put a little container of it, like in a little bit of a porcelain or a clay heating dish, and then you heated it gently with a Bunsen burner. Eventually what will happen is this compound will decompose. Okay, so recall what a decomposition reaction would be. The bigger molecule breaks apart into smaller pieces. Well, you can get this thing to release a water molecule, and if you can kind of in your head do a subtraction of H2O, you actually end up with calcium oxide. If you can't quite see that, let me draw it for you. So here's a calcium. Pretend there's a calcium ion. Okay, so it's +2. And then I've got here, there's a hydroxide, OH, kind of hanging off of one side of the calcium. And then here would be another OH off the other side. So imagine for a second, if you were to subtract a water molecule, okay, so you heat this thing up and you get it to fall apart, all the pieces to kind of come apart. If you were to remove this guy, and this guy, okay, so you remove those three parts, what would you get? Well, you get an H, another H, and an O. You would get H2O. You remove H2O. You would be left with those two, which would be calcium oxide. And so you can take calcium hydroxide and heat it, and you can get it to decompose into calcium oxide and water. And then if you remove all the water, you're left behind with calcium oxide. Calcium oxide is without the water molecule, and therefore it is an anhydride now. So anhydrides are compounds that have had a water removed from them. There's lots of examples. One of the things that you are going to recognize for all of these anhydrides is you're going to recognize that they always have some atom on the left-hand side, and then they've got oxygen as the partner. Okay, so they tend to be binary molecules, just two different types of elements, and they will have something attached to an oxygen. So if I start listing a whole bunch of things, so if I list sodium oxide, potassium oxide, magnesium oxide, calcium oxide, cesium oxide, carbon dioxide, carbon monoxide, nitrogen dioxide, sulfur trioxide. And I mean, the list can go on and on and on and on and on. You'll notice that every single one of those things that I wrote down, regardless of what I put on the left-hand side, they ended in oxygen. And even their name was something oxide, carbon dioxide, magnesium oxide. So you end up with an oxide. And all of these things can result from removing water from a different compound, and thus they are anhydrides. Okay? You don't just get anhydrides by taking a compound and removing water from it. You'll also notice that any of these things, you probably recognize this, any of these compounds that I put up here on the board can also be formed through a synthesis reaction between the element that's on the left and oxygen. And anytime you're reacting with oxygen, you're burning something. So if I were to take a chunk of sodium and burn it in the presence of oxygen, you would form the ionic compound sodium oxide. If you were to take a piece of calcium, burn it in the presence of oxygen, it will form calcium oxide. If you take nitrogen gas and burn it in the presence of oxygen, you could get nitrogen dioxide. You could also get nitrogen monoxide and nitrogen trioxide, and there's other things that also form. And they're the covalent ones. You'll notice the ones on the right are all covalent. You get different kind of bonding combinations. When you're talking about the ionic ones over on the left-hand side, those tend not to have variations. They can, but they tend not to have a whole lot of those variations, just because the oxide ion, O-2, and the cation that you put them with, say sodium +1, they tend to form always the same thing because of that outer shell concept. Okay, whereas the covalent bonding, there's kind of some weird and wonderful ways that the electrons get shared. So covalents have kind of a little bit more flexibility and therefore variety in the formulas of the compounds that get made. But I want you to understand that you can make an oxide compound, which is known as an anhydride, either by taking a larger, more complex ion, and if it has the right kind of formula to it, you can heat it, remove water, and you end up with the oxide. Or you can synthesize the compound by burning or reacting an element in the presence of oxygen. Okay, so that concept, first of all, one, like how are you going to identify these anhydrides? They typically are, not typically, for Chem 12 purposes, let's kind of keep it simple. For Chem 12 purposes, they're always binary compounds, so two types of elements. Two, they always have oxygen on the right-hand side. Okay, so they're binary, but one of the two elements that are in that binary compound will be oxygen. Okay, so if I had sodium chloride, that's not an anhydride. Okay, from our Chem 12 perspective. Okay, so that's kind of the what are they and identifying what they are. Of course, you should also have an understanding of where they can come from. And the primary one that you're probably going to remember moving forward is if you burn an element in the presence of oxygen, you will make an oxide compound of it, and that will most likely be an anhydride. Okay? So, what are the two categories? Oh, and I maybe shouldn't have erased that. So there are two categories, and the two categories are acidic anhydrides and basic anhydrides. Okay, so I'll put the two categories up here. So acidic and basic anhydrides. So the acidic ones have a very common identifying feature of all of them. The basic ones have a very common identifying feature of all of them. And I'll just say this all the time. So if we keep in mind that anhydrides always have oxygen, the two categories are based upon what the other element would be. Okay, so both of these have oxide. Okay, so oxygen is the second element. The acidic ones have a nonmetal plus the oxygen to form the oxide, which kind of defines anhydride. So the acidic anhydrides are a nonmetal with oxygen. So carbon dioxide or sulfur dioxide, those would be acidic anhydrides. The basic ones, therefore, are metal plus oxygen. Now, the ones that we're particularly concerned with, there's a certain category that we're concerned of here in Chemistry 12. And so when you're talking about the acidic anhydrides, and I'm going to go through these, there are three very important ones that we expect you to know something about, and there's reasons why we expect you to know something about them. So I'll go through those three. For the basic, the metal with the oxygen, so the basic anhydrides, we're concerned with the alkali and the alkali earth oxides, okay? Particularly those two categories. You can have other oxides. You can have aluminum oxide, zinc oxide, copper oxide. You can have all of those oxides as well. Those types of metal oxides tend not to hydrolyze as much as the alkalis and the alkali earths do. And so they, I guess, aren't quite as prevalent when we're talking about the action of these anhydrides when they hydrolyze. So we're going to keep that in mind, Okay, so let's talk about the acidic ones first. So the acidic anhydrides are nonmetals with the oxide attached to it. And so I'll start with carbon dioxide. So carbon dioxide is an example of an acidic anhydride, or a non-metal covalent oxide. Okay, so there's carbon dioxide. This is what they typically do. When you take these covalent oxides and you bubble them through water, because they're typically gases at room temperature. So you bubble them through water, they will dissolve in the water. A gas will dissolve into water if you bubble it in there under pressure. And so now, not all of it's going to dissolve in there, but some of it is going to dissolve. It'll go from a gaseous to an aqueous form. And some of the gas will just kind of bubble out. Before it actually dissolves into the water, it will bubble out and go out the other side. Now, of course, if we were trying to get it to go into aqueous, we would obviously have different containers and different properties, and the environment would be a certain way to get it to do that. But if I take this carbon dioxide and I bubble it through some water, what it will do is it will chemically react. So some of the aqueous carbon dioxides that float around in the water, so you get it to dissolve and they float around in the water. I should actually write a little AQ here. Little aqueous carbon dioxides will react with some of the waters. Now, this reaction does not go 100%. This forms an equilibrium. And for those of you who have done your biology 12 and you've done your respiration already, this happens, for example, in your blood. Okay, so out at your body cells that are producing tons of carbon dioxide, well, where does that carbon dioxide go? Well, it actually dissolves into the water that's in your blood. And it actually chemically reacts, partly. And then there's enzymes and stuff involved as well. But what does that carbon dioxide plus water reaction actually make? Well, when you're talking about the covalent oxides, acidic anhydrides, it's almost as if, remember that an anhydride was taking out a water molecule. So when you reintroduce a water, like they bump into each other, they can reform that compound from which the water was removed in the first place. Okay, so I've put a water back in to this molecule. Now, what they typically make is an acid. So you can kind of, knowing that you're just taking the water molecule and smushing it back together with that acidic anhydride, you just take all the atoms and combine them into one, you synthesize them into one giant molecule. So that means you're going to write it in the form of an acid with all the atoms kind of smushed together. So you've got two H's. There's two H's. You've got a carbon. There's a carbon. And now you've got three oxygens, which is carbonic acid. H2CO3 is carbonic acid. It's a weak diprotic acid. If it's in water, there's a Ka that you can look up on the Ka table. It will then, like the H2CO3 will then float around in as a molecular covalent compound dissolved in the water. It can then bump into water molecules. It can donate an H and it can produce hydronium. And so this thing will actually produce hydronium in solution. Now, if I was sitting here in class right now, I'd be doing a demonstration where I'd have a beaker of water, and you can do this. I'm at home, and I don't have these things at home. Obviously, I have water. I would take a beaker of water. Into the water, I would drop some bromothymol blue, which is an indicator, which you may have used before. And it's green when the solution is neutral, which you would anticipate. Water is just going to be neutral, so it kind of comes out green. And when the water becomes basic, it turns blue. And when it becomes acidic, it turns yellow. And so, like if I'm in a class, I have this big beaker of water. And so I take the big beaker of water and with a straw, I blow bubbles into the beaker of water, and it kind of froths and it kind of goes all over the place and it spills and everything else. And everybody kind of laughs at me because I make myself wet. But eventually what happens is that solution goes from green, which is neutral, to really quite yellow, because the carbon dioxide that I'm breathing out in my breath every time I breathe out is dissolving more and more and more into the water, thus doing this hydrolysis where H2CO3 is being made, which then donates a proton to water and it makes hydronium. So as I'm blowing bubbles into the water, it's making more and more hydronium as I go along, thus bringing the pH down and down and down. And so you make it acidic. Okay, so you can make it really quite acidic actually if you just keep sitting there blowing bubbles into the water. Now, this reaction is really quite important because, of course, I can demonstrate by blowing out the carbon dioxide. But I want you to imagine for a sec that there's a lot of animals on planet Earth, and every single animal on planet Earth is doing cellular respiration, and they're taking oxygen, and they're burning sugars, and they're pumping out carbon dioxide all over the place. All animals on Earth are pumping out carbon dioxide constantly. Plants love the carbon dioxide, and they kind of turn it around and turn it back into oxygen, and we breathe that in, and it kind of goes back and forth, back and forth. Meanwhile, though, there's a lot of carbon dioxide that's out there in the atmosphere. And so animals are obviously producing this constant amount of carbon dioxide. Now, interestingly, animals and plants for a very long period of time have been in this kind of neat little balance where the carbon dioxide produced by the animals is used by the plants and they produce oxygen, so the two are really closely connected to each other. When more and more plants are on Earth, there's going to be more oxygen. The animals are going to get bigger, become more populated, whatever. There's more oxygen in the atmosphere. Animals then start taking up that oxygen and they turn it around into carbon dioxide. And so the carbon dioxide level might go up. And then the plants start to kind of take over again. So there is this kind of natural back and forth. But generally speaking, the carbon dioxide level, if you're talking about a 10 million year span, the carbon dioxide level is fairly constant in the atmosphere. It has slight fluctuations, and you'll see in the geological history that it does change a little bit based on kind of geological events that are going on Earth. Needless to say, there's carbon dioxide in the air. Well, the carbon dioxide that's in the air is in contact with the surfaces of a lot of bodies of water. So the ocean, lakes, rivers, your tears, raindrops as they're falling to the earth, any kind of water that is in contact with the air is coming in contact with carbon dioxide, obviously. So every single little bit of water that is touched by air will have some carbon dioxide in it. Well, depending on how much carbon dioxide has time to get in there and gets mixed up and how far away from the air it is and things of that nature, you're going to be making this. So things get acidified. Water gets acidified when it's in contact with air. There is a kind of a naturally occurring acidification of water that's in contact with air. So for example, when you pour water out of a tap, it is not pH of 7. It just isn't. It's been in contact with the air. I mean, it's in a reservoir somewhere that's in contact with an air. It's kind of bubbling through pipes, which they're not airtight. So the air is going to go through there. It comes out of your tap in contact with the air. It sits there in a beaker in contact with the air. It's actually being mixed with air. Well, it's going to have some carbon dioxide dissolved in it. And so a natural amount of carbon dioxide is in all water that's in contact with the air. And if that's the case, then there's a natural amount of H2CO3. And so there's a natural acidification of water bodies around the Earth. Okay, now, generally speaking, the amount of carbon dioxide is the same throughout the Earth. So the amount of acidification then depends on temperature and salinity and some other things. But generally speaking, they all have it. So if you measure the pH of your tap water, it's probably going to be in the neighborhood of 6.8, 6.7. It might even get as low as 6.5 or 6.6, somewhere in there. So even at 25 degrees. So that idea that your water should be pH of 7 if it comes out of a tap, no, that's not true. Water that has not been in contact with air and is distilled water will have a pH of 7. But if contact with air occurs, the carbon dioxide is going to acidify it to a certain degree. So when someone's talking about the acidification of, say, the oceans, for example, the rising carbon dioxide levels in the atmosphere right now, where's that acidification coming from? Well, if the atmosphere has a growing amount of carbon dioxide in it, even if it's a very subtle amount, then that means that this reaction, this hydrolysis reaction, is going to produce more carbonic acid. And so there will be more carbonic acid in the oceans. Now, it's a very subtle amount. It might change the ocean pH from a 6.8 to a 6.74, or not even. But some of the living things, like corals, for example, have evolved to the point where they have a very small pH range in which they can actually exist. And so this change in the carbon dioxide changes the pH of the ocean through this process. Okay, so this one's an important one from the acidification of water perspective. Okay, so where do you get carbon dioxide from? Like, where does that actually occur? Well, carbon dioxide has three major sources here on Earth. Number one, animals. We're producing it all the time, right? Two, volcanic activity. Okay, so anything that is like geological. So carbon dioxide is coming out of volcanic vents. It's one of the gases that comes out of there. Okay, because there's carbon compounds that are actually down in the rock layers that get recycled through volcanic activity. And so carbon dioxide is going to be one of the products that comes out of volcanic activity. And so you'll see this fluctuation in carbon dioxide levels that kind of go along with, from a geological perspective, the volcanic activity of the Earth along the way, which, you know, Earth science from that perspective in geology is kind of an interesting thing to follow those fluctuations in Earth's history. So that's the second one. The third one is through the combustion of carbon compounds. Well, carbon compounds means organic. So anything that is organic is when you burn it, right? Carbon, you burn, remember what I said earlier, you will synthesize a compound that is a carbon compound with oxygen. So carbon dioxide, carbon monoxide. Carbon dioxide if it's a highly efficient one. So you'll get carbon dioxide when you're burning that. So what types of things are we talking about? What types of things are organic compounds that we're burning? Well, I mean, things that were just recently alive, like burning wood and things of that nature. That is obviously organic material, so you're going to produce carbon dioxide. But probably more important for our industrial and our environmental concerns are fossil fuels, which there are giant fossilized reservoirs of carbon way down in the earth that we have dug out of the earth. Coal and natural gas and all the different petroleum products that we pull out, oil. And we've learned that you can burn them because they're carbon-based, and so you can burn them and get energy from them and use that heat source for a whole variety of different things. Product of that is obviously carbon dioxide. And so the fossil fuels is kind of the third kind of major way that we're producing carbon dioxide here on Earth. And the acidification of any body of water is due to whatever level of carbon dioxide is out here. Okay? So that's carbon dioxide. The second one that I wanted, or the second and third one that I wanted to make note of, SO2 and SO3. I'm not going to put aqueous because we're going to assume that they're aqueous now. So SO2 and SO3, again, if they're anhydrides, you take the water molecule and smush it back into the SO2 or the SO3, and what does it form? Again, they don't do this 100% necessarily. So this guy becomes H2SO3, and this guy becomes H2SO4. And in particular, H2SO4, you should recognize as being one of our strong acids. So if you make H2SO4 through this process, if you have SO3 and you bubble it through water and you make it hydrolyze, you're going to form sulfuric acid. Well, sulfuric acid is kind of It's one of the granddaddies of all acids. So it's a strong acid that is quite nasty. Okay, so you don't want to be making a whole heck of a lot of this stuff, unintentionally anyways, in your water sources. SO2 makes sulfurous acid, which isn't quite as bad, but it's still pretty darn bad. I mean, it's certainly a stronger acid than H2CO3. Now, where does SO2 and SO3 typically come from? Okay, so it comes from, okay, so this is kind of, I'm narrowing it down a little bit here. So whenever you burn organic material has a whole bunch of different, I'm not going to say contaminants, they're elements that were always part of the organic material. But two really kind of critical ones that you should know through your biology would be sulfur and nitrogen. Okay, so SO2 and SO3 are covalent oxides or acidic anhydrides that result from the combustion of sulfur compounds. And so if you have sulfur in your organic material, which you do, you'll have sulfur content in fossil fuels in particular. So if you combust that sulfur under high heat, you are going to produce sulfur dioxide and sulfur trioxide. So where's the sulfur dioxide and sulfur trioxide coming from out there in the world? So one, it's not being produced by animals, so that's different from carbon dioxide. But it is definitely being produced by industry, because the sulfur content in the different petroleum products that are used in industry, it's higher than it would be if you're talking about, say, in automobiles, because the refinery process has a little bit more sulfur in it. And so industrial processes that burn fossil fuels, they tend to have a little bit more sulfur in them. They produce a little bit more sulfur dioxide and sulfur trioxide. The other thing is you get a lot of sulfur oxides and trioxides coming out of volcanic activity again. Okay, so there's a lot of sulfur coming out of volcanic activity. If you've ever been to a hot spring somewhere, you'll smell the sulfur, right? It has a very strong sulfury type of smell. Well, that's actually the sulfur coming out of the volcanic vent that is actually heating that hot spring. So there's sulfur kind of bubbling up through. That when volcanic activity occurs, there's obviously a lot of heat associated with it. And so you get, in that plume of smoke that comes out of volcanic activity, there's a lot of sulfur dioxide and sulfur trioxide. Well, if that stuff then dissolves in water, you're going to end up getting H2SO3 and H2SO4. So where does that typically occur? So what I've just mentioned to you are two sources where the gases, the SO2 and the SO3, are produced, and they end up in our atmosphere, right, floating around. They're somewhat natural with volcanic activity, but I mean, let's face it, there's not so much going on in volcanic activity that these things are pervasive in the atmosphere. So the one that is above and beyond what the natural production of sulfur dioxide and trioxide would be industrialized combustion. Okay, so we're making these two acids right here. The other one that I want to get into, and the mechanism by which this one works, like the actual chemical equation for this one, is not quite super simple. So I'm going to put it under the category of nitrous oxides. Okay, so NO, NO2, and NO3, also N2O5 and N2O4. So nitrous oxides also hydrolyze. They are also, because nitrogen is part of organic material as well, they are also the byproduct, and oftentimes not producing tons of energy, so the byproduct of industrial or combustion. Okay, so let's say, well, the word is anthropogenic, so human-created combustion processes. So you're going to get the nitrous oxides being produced in slightly more refined fossil fuels. So Industrial fossil fuels aren't super highly refined, and so they tend to have a high sulfur content. But in more highly refined fossil fuels, you will get less and less and less sulfur, but not necessarily the removal of the nitrogen from them. And so those fossil fuels tend to go into our automobiles. And so the cars that we drive around, the trucks that are being driven around, and most of the airline or airplane fuels that are out there as well, they will still have a fairly high nitrogen content. Of course, you can pay for the really expensive fossil fuel where it's been super highly refined and all those nitrogen compounds have been removed. You're talking about, like, if you were a race car driver or something like that, then you're not talking about, going to your local Chevron and filling up. You're talking about hundreds, if not thousands of dollars per liter/gallon. So super highly refined. We're not doing that. We're going to, unless you've got an electric vehicle, you're going to the gas station, you're filling up, and that's still going to have some nitrogen content in it. So when you burn it in your car, out the tailpipe, and you can't see it, will come some nitrous oxides. Okay? And so the nitrous oxides go up into the atmosphere, or they come in contact with bodies of water all over the place, and they also react. Now, like I said earlier, the mechanism that these guys have to produce what they produce is really complex. Like, it's multi-step mechanism. So let's just kind of cut to the chase. Two acids get made. Nitrous and nitric. Again, nitric is one of our 6 strong acids, so nitric is a bit of a doozy. HNO2 is, again, it's a weak acid, but still, it's way stronger than H2CO3. So what I want you to notice here is that these ones in particular, okay, the ones that I just put that little bracket around, those ones in particular, the hydrolysis of the sulfur oxides and the nitrous oxides, those ones in particular make some pretty nasty acids. Okay, so they make stronger acids. A strong acid, as a matter of fact. Okay, so that's number one. Number two, that both of those things are the primary source of them tends to be from the combustion of fossil fuel. Okay, tends to be. So if you're talking about industrial processes, those industries will be pumping out a lot of SO2 and SO3 and a lot of NO2, NO, and NO3. So those things get made quite frequently through industry. Okay, and of course, industry's being regulated now. I mean, there's a lot of different environmental movements to have governments reduce the amount of sulfur and nitrous oxides that are being produced by industry. Well, why is that? Because those industries are producing high levels of these gases, of these acids, when they come in contact with water. So if you're in a highly industrialized area and you're producing and the industry's producing a lot of these gases, and they're not being removed before those exhausts come out of the smokestack or something like that. So if they make it into the atmosphere, they're going to float around in the atmosphere, and they're going to obviously concentrate or move off in the distance, but they're going to be sitting there circulating and moving around and mixing with water, particularly once that water starts to fall to the earth in the form of rain. And so these chemicals find themselves in the rain, which is where that idea of acid rain comes in. Now, acid rain is defined by rain that has a pH actually less than about 6.4, because rain can be naturally acidic because of the natural amount of carbon dioxide that's up there in the atmosphere. So no one's going to freak out when your rain actually measures a pH of 6.5, because it's fine. I mean, that's just probably from the carbon dioxide that's floating around naturally in the air. But the actual acidic rain, like, you can even get down into like the 5s the low 5s, even the high 4s, where you collect some rain and it from an industrialized area that is producing a lot of these gases, and you're going to get quite acidic rain. And so that's the definition of acid rain, is not just below 7. It's actually below a certain level, kind of beyond what would be reasonable for the carbon dioxide that's in the air. So don't ever think that carbon dioxide causes acid rain. It does acidify rain, but it acidifies it, but it's a natural thing. You're not going to get rid of the carbon dioxide that's out there. If you did, you'd kill all the plants because they need it, right? Which would kill all the animals, which life on Earth would stop if we did that. So we need a certain amount of carbon dioxide. So the water is going to be naturally just a little bit acidified by that amount of carbon dioxide. It becomes an issue, though, once these things get out there, which tend to be the products of the industrial or transportation combustion. Now, volcanic activity produces these things naturally as well, but the amount that is produced by volcanic activity is really small compared to what industry is actually producing. And so therefore we're concerned about how much industry is producing. So there's your acidic anhydrides. Okay, so certainly carbon dioxide, SO2, SO3, and then the nitrous oxides, those ones are of particular concern. So let's go to our basic anhydrides. Which are not as much of an environmental concern because we tend not to be producing a ton of them through the burning of fossil fuel. They are more naturally occurring because metals like to react with oxygen. And so you tend to get a lot of oxide compounds that are out there just kind of naturally in rock forms around on Earth, right? They're just naturally part of rock. So we're not producing a whole heck of a lot of these things unintentionally, okay, as it were. So the basic ones were the metal plus the oxygen. And as I mentioned earlier, the alkalis and the alkali earths tend to be the really important ones. So I'll write down a couple of the alkalis. Certainly sodium oxide. Let's do rubidium oxide just because it's different. And then we'll go with magnesium oxide and calcium oxide. So the idea is that these are anhydride compounds, so water has been removed. So by hydrolyzing them, we are essentially, what we're doing is we're putting water back into them, right? Anhydride is removed, so it's without water. Hydrolysis will be reacting it, so it resynthesizes with that water. So each one, if you take a water molecule, and add it back in, what you're going to get in every single case, and it's quite simple as a matter of fact to have this stuck in your head so that you have it memorized, is you'll make the hydroxide of the cation. So if it's sodium oxide and you hydrolyze it, you put it into water, you kind of mix it up a little bit, it actually reacts to form the hydroxide of sodium, aka sodium hydroxide. So every single one of them, you are making the hydroxide, and then you'll see what happens is the balancing actually is pretty straightforward. Like you'll see, it's quite a simple thing to do. So watch what happens here. So I've got a sodium hydroxide. I almost didn't even look over here at what the subscripts were. I just knew that the hydrolysis of sodium oxide, being a basic anhydride, or metal oxide, will make sodium hydroxide. So I wrote down the formula of sodium hydroxide. I know that off the top of my head. Then what happens, actually, before I do any balancing, I'm just going to go through all four and just write down the products. So rubidium oxide, hydrolyzing, reacting with water, will make rubidium, which is +1, it's an alkali. Hydroxide is -1, rubidium's +1, so it'll be RbOH. Magnesium being +2, magnesium hydroxide will be MgOH2. I'm not worried about what the subscripts were over here. I know the formula of magnesium hydroxide is MgOH2 because magnesium is +2 and hydroxide is -1. So I know that's the formula of it. I will balance it to make sure it all works out. Calcium oxide is also +2. Therefore, I get calcium hydroxide. So then I go back and I say, okay, so let's balance these guys. So over here, I've got 2 sodiums. I need a 2 in front of that. So the sodiums are balanced. I have 2 oxygens, 2 times 1, that's 2. Perfect. 2 hydrogens, 2 times 1 is, okay, balanced. Okay, so all I needed to do was put a 2 in front of that. This guy is exactly the same. This guy, 1 magnesium, 1 magnesium. 2 oxygens. Well, that times 2 gives you 2. 2 hydrogens. Well, that times 2 is 2. That guy's balanced. And so is the calcium hydroxide one. So the actual balancing of it is fairly straightforward. So if you can remember that a metal oxide slash basic anhydride, when you put them into water, they form the hydroxide of the cation. You can write the formula of the hydroxide and balance it to get the actual thing. The balancing is pretty straightforward. Remember that it makes a hydroxide. Now, once you've made a hydroxide, then they proceed to act as Arrhenius bases. Okay, so if I take, if I now take, how am I going to do this? So I've made this. Okay, so sodium oxide in water is going to make 2 sodium hydroxides. Well, sodium hydroxide then is a soluble compound which forms that. Well, you're producing hydroxide, and so therefore that solution is going to be basic. If you take sodium oxide, like if you make sodium oxide and you take the white powder that sodium oxide is and you dump it into water and kind of swirl it around, it doesn't actually dissolve super well. Oxides are not very soluble. I know sodium is a soluble thing, but it's not super soluble. You mix it around in the water, and eventually what will happen, the whole thing will eventually disappear because it will eventually all turn into sodium hydroxide and completely dissociate into these 2 ions. And so sodium oxide will eventually make the solution really basic, as a matter of fact. Okay? Same, the rubidium hydroxide one, same thing, so I'm going to erase it. These guys are the same. So the magnesium hydroxide one, though, this is not a strong base. It is a low soluble hydroxide compound. So magnesium hydroxide, not quite as much. So I've got the equilibrium arrow up there. So magnesium hydroxide forms, but it doesn't make nearly as much hydroxide as, say, something like sodium hydroxide would make. So you can make magnesium oxide, mix it around in water. It doesn't nearly dissolve like the sodium oxide will. And so you can swirl it around all you want. It's not going to fully disappear, but you're still going to make it slightly basic. Okay? And that's what you're going to actually see. So if you've ever, in a class before, or in Chem 12 even, you've taken a piece of magnesium and you've burned it in a Bunsen burner and you get that white powder that gets produced at the end, if you allow that to fall into a beaker of water, and then you stir it up with a stirring rod, the pH will become quite basic, right? Again, so if you take some bromothiamyl blue indicator, and it was in the water before, it'll start green. You throw in the magnesium hydroxide that is formed from burning magnesium, stir it up a little bit, it'll turn really blue because it will become quite basic, even though magnesium hydroxide is not a super strong base. It will become quite basic. Okay, so those are the metal oxides slash basic anhydrides. Not quite as significant from an environmental point of view because we're not out there like burning sodium and burning magnesium all over the place, right? Like that's not what we tend to do. I guess in some chemical industries, you're making oxide compounds, oxides of metals, that then kind of maybe get dumped, probably illegally, into bodies of water, which would then make them basic. However, that's not a common event going on around the world. So it doesn't get quite the attention that the covalent oxides get, or the acidic anhydrides. So that's the anhydrides, and that is the entire unit of hydrolysis. So coming up next is going to be our titration unit, which again is going to be kind of awkward because it's just me and the whiteboard and my drawing abilities in my room here at home without the equipment. So this could be a fairly interesting set of lectures, but hopefully I can get across to you the theory that's associated with some of those lab techniques, some of the things you would be watching for when you are doing, eventually you get yourself into a lab and you're doing a titration, but more importantly, kind of the theoretical side of things, and you'll see that there's some indicator choices and pHs at equivalence and graphing that you have to learn about. So we'll go through all of those things in the titration unit. Okay, until then, we'll see you later. Take care of yourself. Make sure you're keeping your social distancing, and keep yourself safe and healthy. Okay, we'll talk to you later.